So I think it was the visiting professors programs folks who were interested in a talk on exploratory factor analysis. And so Tor and I were talking about this, and I said that, okay, I'm happy to give a talk on exploratory factor analysis because I have the slides and I've done it several times, but I'm also going to then insist that I get to give a talk on VARCLUS, SAS PROC VARCLUS, because I really don't use exploratory factor analysis very often anymore. And so what I really use, especially for large models, lots of items, I use SAS PROC VARCLUS because it works a whole lot better. This is what I consider to be part one of a two-part talk, and this is kind of given as background because exploratory factor analysis is very well known and used a lot. PROC VARCLUS, hardly anyone knows anything about it. So it does make sense to start with EFA. And EFA is useful in some circumstances, and I even use it in conjunction with PROC VARCLUS, which I'll talk about how that happens next month. Okay, so as an overview, EFA is one form of what's known as the common factor model, and the first couple slides here are going to be talking about the common factor model generally, and that includes exploratory factor analysis as well as confirmatory factor analysis, but I'm not going to talk about confirmatory factor analysis, but just to give you some bearing here that what I'm talking about here is a little bit broader than EFA per se. But the whole idea is indirect observation. So in any field of scientific inquiry, there's going to be some things that you're interested in measuring that are not directly observable. So in behavioral things, it could be private behaviors that aren't observed by anyone except the actor. But it could also be things that are inherently unobservable, like someone's personality or their intelligence. You can see some kind of indirect offshoots of those kinds of traits, but they're not directly observable. And I like to point out that physics is full of indirect observation. And they don't use exploratory factor analysis because they have other means of indirect observation. But it's just part and parcel of science that not everything we're interested in can be directly viewed. And so in the behavioral sphere of things, indirectly measured constructs are often called latent variables. And in the context of the factor analysis model, latent variables are typically empirically identified by multiple fallible, observed, or what are sometimes called manifest variables. So we have some constructs that we'd like to measure, but we can't observe them directly. And so our approach is to collect information on what can be observed and try to pull it together, so to speak, or pool that information together in a way that will allow us to hopefully claim that we are measuring the latent variable that we hope to measure. And that gives us an approach to do that. So a measurement model, a common factor model, is a form of a measurement model. It relates the latent variables to the manifest variables. And the idea is that, so say you have a personality instrument, and your personality dimension, say it's gregariousness, you have a bunch of items that you think as an investigator are fallible but decent indicators of gregariousness. You sample a set of respondents to respond to your items, and you're asking them, how much does this item describe yourself? And the idea is that the person's level of gregariousness causes their response to the item. If they think that the item which describes a gregarious person is like them, then they might say, well, yes, this statement describes me. But if they think it's unlike them, they would respond that this is unlike me. So common factor model is really a causal model, because the idea is that the latent variable is causing the responses to the observed items. And if we have multiple observed items or manifest variables per latent variable, then we can fit a measurement model that can be empirically validated. We can assess the degree to which it can replicate the observed data. And so we can get basically a goodness of fit test. What does common mean in this context? What it means is that the common factor model is only interested in working with the variance that's shared among a set of items. So each item is going to have, you could think about splitting the variance up or decomposing the variance for any item into the variance that's shared with at least one other item, and the variance that's completely unique to that item. So this common factor model is not interested in the variance that is unique to each item. It's only interested in working with the variance that's shared. Okay, so just checking the notes there. Okay, so the goals of the common factor model, first and foremost, is to assess a form of validity, its construct validity. And that's the basic idea is there, does my instrument measure the latent variables that I hypothesize it measures? And a lot of people don't, when people think about validity assessment, they think of convergent, discriminant, predictive, concurrent. A lot of times you show someone a factor analysis, the results of a factor analysis model, and it may completely confirm your hypotheses about the number of factors, the configuration of items within each of those factors, etc. And they'll say, well, but you haven't done any validity assessment. Well, they're wrong. Some of the strongest evidence that you can have for validity is a well-fitting factor analysis model that corresponds to your hypotheses. So it's a very strong form, actually, of validity assessment. But in addition, more secondary goals are to have some kind of data reduction, have a more parsimonious set of constructs, and then, to provide empirical justification for creating composite scores, which are more reliable than individual item scores. So it's important secondary goals, but the primary goal is construct validity. So I just wanted to point out that the common factor model is more than 115 years old. And it's come a long way since then. I think in the old days, people did their entire dissertation with an adding machine to perform a single factor analysis. And now we just do I could do 20,000 a day if I really wanted to. So here's a conceptual example. It's consumer confidence. So these are actual items that people ask. So you're listening to the news and they're talking about consumer confidence. Is it up? Is it down? These are the kind of items that they ask people. They sample some people and they ask them about their kind of economic expectations for the upcoming 6 months, just in terms of the total economy. And they say, it's going to be worse, the same, or better. And then they ask their purchase plans within 6 months. So they're going to purchase any of these items. And that's basically a hypothesized two-factor model. There's like expectations and plans to buy. And there's 3 manifest items for each of those. And so this is like a configuration. I've got 2 latent variables. The curved arrow with the double-headed arrow shows that they're correlated. or we expect that they're correlated. And then these single-headed straight arrows depict the causal effect of the latent variable on the responses to the observed items. And so in the process of fitting, collect some data and then try to estimate these model parameters, I will get an estimate of the correlation between the two factors, and I'll get estimates of these effects of the latent variables on the items, usually represented as correlation coefficients. In a simple case like this, standardized factor loadings. They can be bigger than one in a more complicated model because they really are standardized regression coefficients. But in simple models, you can think of them as correlation coefficients. And oftentimes, you know, your program for fitting a factor analysis model isn't going to give you a pretty picture. It'll give you some kind of matrices. And so in this case, there might be, you know, the program would say factor 1 and factor 2. It would be up to you to label those. But it'll give you basically, in this case, correlations, standardized factor loadings between each factor and each item. And in this case, this is a made up example, but if we had a pattern like this, it would show that the kind of relationships between items and factors correspond at least to what we hypothesized, that the expectations related items tend to be more strongly related to one factor, and the plans to purchase items tend to be more strongly related to the second factor, and that all of these other non-highlighted kind of regression coefficients are relatively weak. So based upon this, this pattern of results, I might look at the items that are related to the first factor and then come up with a label that I think describes the first factor, and the same thing for the second factor. So if I started with this conceptually as a kind of a priori position, and I ended up with this, then I'm in a pretty good position to say, hey, you know, I've got support for my empirical support for my hypothesis about the measurement model that is appropriate for these 6 items. Okay, so usually people ask me, how is it possible to estimate the relationships between something that isn't observed and something that is observed? And it's just a matter of explaining, having a more parsimonious model, a model that's more parsimonious than the data, and then checking how well the model can reproduce the observed data. So you start with your input data. Usually it's correlations, item correlations or covariances. And then you kind of iteratively search for these kind of relationships between, well, you specify a number of factors as well. And then you search for relationships between factors and items that attempt to at least reproduce the input data, which is the inter-item correlation matrix. You can compare the model reproduced correlation matrix to the observed correlation matrix. And if they're close, it suggests that your model is doing a pretty good job of explaining the observed relationships. And to the extent that your model is parsimonious, that's evidence that you're on the right track. So here's a simple example. Let's say I had 4 items and I think that there's a single factor that is represents those 4 items or is represented by those 4 items. I've got an input correlation matrix, the 4x4 inter-item correlation matrix, and I'm going to search for 4 factor loadings, these relationships between the factor and each item. So I've got a 4x4 correlation matrix that's got 6 inter-item correlations. I'm going to try to explain those with 4 factor loadings. And typically, what you can do, if I want to know what the model implied correlation between item 1 and item 2 is, I can multiply this standardized factor loading by that standardized factor loading, and that's the correlation, the model implied correlation between item 1 and item 2. And I can do that for all 6 pairs. And so if I can find a set of factor loadings that does a good job of reproducing these 6 correlation coefficients that are pretty good matches to the observed data, then I've got a more parsimonious representation of those inter-item correlations with just 4 parameters. Now, this is a simple example. If I had 10 items and a single factor, then I would have 45 inter-item pairwise correlations that I was explaining with 10 factor loadings, if the model was able to do that. Now, if if my model is wrong, if there's really 2 factors or 3 factors, then probably it's going to do a 1 factor, but a fit of 1 factor model, it's probably going to do a poor job of reproducing the data. So I will have evidence that my idea that there's a single factor is probably wrong. So this is just a little bit more fleshed out. If I estimated factor loadings of 0.5, 0.6, 0.7, and 0.8, these would be the implied correlations between the items. And then you can compare the implied correlations to the actual ones, and there's like a chi-square goodness of fit test that you can do to see whether or not you've got good or poor goodness of fit. In this case, a significant chi-square suggests a significant lack of fit. So what you're looking for, if you're doing that kind of testing, is a non-significant chi-square. So again, implications of empirical support for a common factor model are, it's a demonstration of construct validity. And you can have a more parsimonious representation of your data, and it provides empirical justification for creating more reliable composite measures. So optimally, the configuration of a common factor model is specified a priori. So, how many factors, which items are clustered within which factors. And that should be based on theory or previous empirical findings. But sometimes you may start out that way and your hypothesized measurement model isn't supported, and you're unsure how to modify it. But you're not just going to, discard your data. You want to explore it, make the best use of it, and see what you can learn from it. In other cases, there may be occasions where there just truly isn't an a priori measurement model to test from the outset. And if you find yourself in that situation, one option is exploratory factor analysis. So the goal here is to uncover the measurement model or the measurement structure, determine how many factors there are, determine which items correspond to which factors. So this is where I'm making a break from just talking about the common factor model in general, which includes EFA and confirmatory factor analysis, and going off into exploratory factor analysis. So the nuts and bolts here, these are the steps I'm going to cover. And then when I'm done with this, I'm gonna present an example application using the Center for Epidemiologic Studies Depression Scale. So first thing you have to do is, if you're building an instrument, you would start with choosing constructs. What is it that you want to measure? And And then you would have to choose items that you would use to measure those constructs. And in instrument development, you're usually going to craft like a large set of items and then kind of select from the better ones from those. A lot of times it involves qualitative research. So you might have focus groups or individual interviews or key informant interviews to talk with people about how they construe different constructs. Also happens a lot when you might be taking an instrument that has been validated in one population group and you want to adapt it for a different population group. And so you may need to do a considerable amount of adaptation with focus groups in that case. So there's going to be a whole item construction or item selection. And sometimes you are just pulling items from the literature that exist. Maybe there's 10 scales that have items of interest to you and you're just culling from them. Or maybe it's secondary data analysis and the data are the data, but you're not interested in the full set of items that are available in the data set. You're only going to focus on some of them, and so you're going to purposefully select those items. And if you're into primary data collection, then you're going to, build an instrument and administer it to a sample of respondents. Usually, in the case of factor analysis, they're people. And obviously, you're interested in generalizability with respect to your sample, but typically, large samples whose data are applied to factor analysis are not representative samples, but you're still trying your best. Once you have data in hand, you need to compute, or your program will for you, a matrix of inter-item correlations or covariances. And one of the things I want to distinguish here is on the left, there's kind of like a typical correlation matrix with ones in the diagonal. On the right, there's what's sometimes called the reduced correlation matrix, and it has communalities in the diagonal. In the old days in factor analysis, people would actually compute a reduced correlation matrix before they even started their factor analysis. Now it's all done kind of at the same time, typically. So it's not a separate step. But the communalities are basically the variance of each item that's explained by the factors. So before, when I was talking about what's a common factor model, well, the common factor model is only interested in working with the item variance that's shared, at least with some other item. And that any variance that's unique to any item is not considered. And so that's what this reduced correlation matrix is all about. And that kind of takes us into an aside about the difference between exploratory factor analysis and principal components analysis. So just in terms of the matrix algebra, they're really the same procedure, at least in terms of factor extraction, except that EFA works with the reduced item correlation matrix and principal components analysis works with the full item covariance matrix. However, that kind of similarity, mathematical similarity of approach has kind of led a lot of people to kind of overstate how similar these two approaches are because they're really different. EFA it's an end in itself. And like I said, it's a form of validity assessment. It's a form of hypothesis testing. And so the primary goal is to understand the latent structure and to some degree validation. Validation rightfully should probably be in the confirmatory factor analysis camp and not the exploratory factor analysis camp, but still some validity evidence can be ascertained from an EFA result. And the secondary goals are kind of data reduction and composite measures. And again, EFA is a causal model, whereas PCA is really, it's a means to an end. Typically what you're trying to do with PCA is you're dealing with high dimensional data and you need some means of data reduction that you can use to create composite measures. Oftentimes you're not interested in interpreting the composite measures for PCA. You're just trying to like get, you know, hundreds of variables down to a smaller set of covariates that you could include in an analysis or something like that. So PCA is more often kind of dealing with your high dimensional data as a nuisance factor to be tamed. And so if you're interested in understanding latent variables and their relationships to observed variables and testing whether or not your your hypothesized measurement model is correct, then EFA is what you should be doing, not PCA. Okay, the aside is over, and going on to step 4, you need to specify the number of factors. So even though EFA is exploratory, you still need to tell the program how many factors you want to extract. And so if you want to consider, you know, different numbers of factors, you'll have to fit that many exploratory factor analysis models. So some of the ways of determining the number of factors, there's an eigenvalue greater than 1 rule, there's a scree plot, there's chi-square tests of model fit, and under that I include these fit indices. So the chi-square test is really, it's a sometimes called the test of exact fit, and it's pretty sensitive, and it's also sensitive to departures from multivariate normality. So if you have data that are not multivariate normal, it's going to be really easy for your chi-square to be significant, which means it's suggesting lack of fit. And so because the kind of data that are typically input into factor analysis are not multivariate normal, many people are very skeptical of this chi-square. And so people have come up with different kinds of fit indices, which are sometimes considered to be coefficients of approximate fit. And the one I use a lot is called CFI, and we'll get a little bit more into all of these later. I don't know if people know what an eigenvalue is, and there's different ways to describe it. I mean, it's just it's a basic, eigenvalues and eigenvectors are just pretty basic matrix algebra kinds of tools. But one way to think about eigenvalue is that it's the variance explained by a principal component. And so it really is a topic that's more closely aligned with principal components analysis than it is with factor analysis. But you know, it just seems strange to me that both the eigenvalue greater than 1 rule and the scree plot are based upon these eigenvalues, which are really more akin to PCA than to EFA. And they don't work very well anyway, so, but I'll get to those. So this is because your whatever EFA program you might be using probably doesn't report CFI. If your program does allow you to specify maximum likelihood factor analysis, then it's probably going to give you what you need to calculate CFI. So what you need are a couple of chi-squares and a couple degrees of freedom. So this is the purple is the formula. It's pretty simple. You can just do a hand calculation. So this chi-square K and dk are the chi-square and the degrees of freedom from the target model. with however many K factors that you specify. So you specify a two-factor model and ML factor analysis, and it's going to give you a chi-square K with dk degrees of freedom for a test of whether two factors is adequate to explain the data. It's also going to give you a chi-square that might be referred to as a null model chi-square or a chi-square with no common factors. And those are basically, that chi-square is just basically saying that it's a test of whether or not all of your variables are orthogonal to each other. So the idea here is that the chi-square and the 0, sub-0, and d sub-0 are represent a model with horrible fit, because you wouldn't even be engaged in a factor analysis of orthogonal variables. Your whole idea is to create items that are going to be intercorrelated. And so that null model chi-square is just like a baseline for how horrible things could possibly be. And then, so if your two-factor model is just as horrible, then your CFI is going to be 0. But if your two-factor model is doing a really great job of explaining the data that you input, then your CFI is going to start approaching 1. So CFI ranges between 0 and 1, and in my opinion, and in the opinion of a lot of people, CFIs of about 0.95 or greater typically suggest pretty good model fit. So that is what I use in this context, and it's saved me a lot of grief versus doing things like scree plots. And so I'll get into scree plot and eigenvalue greater than 1 rules when we get to the example application. Okay, so that was step 4 before, which was how many factors. This is choosing the factor extraction method. So in common factor analysis, the extraction per se is just an application of matrix algebra. But the difference is in how you estimate the communalities. So how you estimate the diagonal elements of that reduced item correlation matrix. And so the old-fashioned approach is kind of a two-step approach where you first estimate the communalities and then create your reduced item correlation matrix based upon those communality estimates. And then you input that matrix for analysis and you extract your factors. More modern approaches, now that we have reasonable computers, is that there's an iterative kind of simultaneous estimation of model parameters and communalities. And so that's probably, well, who knows what most people do. But there are several iterative approaches, but the maximum likelihood EFA is one of them, and that's what I use because it allows me to calculate the CFI. And then there are literally infinite numbers of factor rotation methods because there are several that allow you to specify real value kind of tweaking parameters, and so there's no end to the number that you could actually come up with. But there's just, even beyond that, there's like such a boatload of them, it's crazy. But you need to have some kind of rotation almost always. There are orthogonal rotation, and within orthogonal rotation, the factors, the rotated factors that you come up with are all uncorrelated with each other. Varimax is probably the most popular one, and it's been around forever. But typically you don't expect your factors to be uncorrelated. And so it's introducing some model misspecification if you impose orthogonal factors. So it's usually better to use what's called the oblique rotation approach. And some of the more popular ones are Promax, Harris-Kaiser, and Direct Obleman. Depends on what kind of software you're using, what's available. But the bottom line is, unless you need orthogonal factors, and there's very few circumstances where you might, you should use oblique rotation. So this is just a graphical example. You know, people used to do rotation by hand. They would get their like graph paper out and their ruler, and they'd start kind of moving things around. So on the left is an orthogonal rotation, so that the black axes are the extracted factors, the blue dots represent the items as projected onto the extracted factors. And then the red axes are on the left are an attempt to find a rotation that is orthogonal, that fits the points, the blue dots, as well as it can. So the two red axes are at 90 degrees. So they're orthogonal. And you know, you can only do so well. Some of these points out here kind of are not right on the axis as well as they could be. But if you relax this idea on the right here, that the two rotated axes, you know, if they don't have to be at 90-degree angles anymore, then you can do a better job of finding a rotation that is going to maximize the relationship between the items and the factors. Okay, so that was the kind of step 1 through step 7, I think. And now I want to get to an example application. And so this is an example I've had around for a long time. It's old in Haynes data, where this is just white men age 50 plus with a CESD as the instrument of choice here. And so the CESD is generally believed to represent 4 factors, and these are the factors over here, and these are the items that correspond to each factor, at least according to what's typically reported in the literature. So steps 1, 2, and 3, well, this is a secondary data analysis, so I can choose to include all of the items that exist or a subsample of them. But just, you know, for historical purposes, the author of the CESD, Radloff, she basically collected a list of common depressive symptoms. So she didn't start with, at least according to her description, she didn't start with this idea that there were a certain number of latent variables that she was interested in measuring, and then choosing items to reflect each of those. She just collected a list of common depression symptoms. And, you know, so that is perhaps a reasonable approach. It may not be the best approach, but it's not a horrible approach, as long as her list of symptoms that she collected were really pretty, you know, broad and encompassing. But it's hard to make sure that you're encompassing, I think, unless you have a top-down approach. Hers was a bottom-up approach. But, you know, as someone who's working with this data set, you might choose to work with all 20 CESD items, or you may be interested in only working with a subset of them for various reasons. Maybe your research question doesn't require all of them. And, you know, so in terms of sampling, there's nothing here to do. It's secondary data. And say we're going to work with all 20 items, we can compute the matrix of inter-item correlations, or actually your factor analysis program will do that. Specifying the number of factors. So again, we've got some choices here. Could be a priori, which would be good, or some empirical options. So for a priori, many investigators, not all, have reported 4 factors. It's pretty typical, 4 factors. For eigenvalues, these are the eigenvalues. You get 1 eigenvalue for each item. There were 3 eigenvalues that were greater than 1, so that suggests 3. This is a scree plot. So basically, this is graphing. These are the eigenvalues versus the components. So it's this 1 through 20 for the x-axis, and these eigenvalues for the y-axis. And then the idea is that at some point there's going to be, you can draw a straight line through some of these eigenvalues, but there's going to be a point where there's a jump away from that straight line. All of this, I guess, I can't remember the name of the guy who invented this, but he was a hiker. So he was just saying, this is like at the base of a cliff. This is the scree down here. And then this is the cliff. And so the idea is you draw a straight line, and then anything on the line is not important, and what's above the line is important. So this suggests 3 factors as well. And then you can look at the goodness of fit and the CFI. So again, a significant goodness of fit test means that you probably haven't extracted enough factors, but also, as I mentioned before, this test is really sensitive to departures from multivariate normality. And so in this case, we see these huge, chi-square tests with tiny p-values, even up to 5 factors. And so it's likely the case that there is some violation of chi-square goodness of fit test assumptions here. And so looking at the CFI, and this is almost always the case, something like this. So it's not surprising at all. The CFI value suggests 3 or more factors here. So the literature suggests 4, eigenvalue greater than 1 suggests 3, scree plot suggests 3, model fit suggests at least 3. So I'm going to consider models with 2 through 4 factors. So then I'm going to specify maximum likelihood EFA because it allows me to get at the CFI. I'm going to specify Harris-Kaiser oblique rotation, but I'm also going to present some varimax orthogonal rotation just to show what you sacrifice if you choose an orthogonal rotation. So here's a 2-factor model with Harris-Kaiser rotation. And so what we get is this large negative factor, all the negative kind of symptoms, and then there's a smaller positive factor with the positive items. And if we look at the interfactor correlations, they're negatively correlated, which makes sense. Because if you're feeling good, you should not be feeling as down. A 3-factor model, here the depressive symptoms and somatic symptom items are all clustered together in 1 factor. The interpersonal factors really only has 2 items. These bolded ones, dislike and unfriendly. The failure item, I think, goes in depressive symptoms usually, but this kind of equivocal nature of the failure item is commonly found in the literature. It's just an item that doesn't really distinguish well between interpersonal issues and depressive symptom issues. So this is a pretty typical finding. But, basically, if we were happy mixing depressive symptoms and somatic symptoms together in 1 factor, this makes substantive sense. And it's a reason why sometimes I think a three-factor solution is suggested in the literature, especially when you get into different cultures that don't make as big of a distinction between depressive symptoms and somatic symptoms as we do in the United States. There's the interfactor correlations between those. And again, the factor 3 was the positive factor, so it's negatively related to the other two. So here is the 4-factor solution. And other than this failure item, it basically is reproducing the 4-factor solution that Radloff first published. So it's doing a pretty good job. And again, a lot of people have this issue in their data, and I think it's a questionable item. But we can see that, the item correlations with the factor, these clusters are pretty tight. These all should be like that means 0.8, sorry, 0.74, 0.47. I got rid of the initial decimal point here. But items are strongly correlated with the factor that they hypothetically belong with, and not so correlated, all these. This is any dot here, the value is less than absolute 0.1. So anywhere between negative 0.1 and positive 0.1 gets a dot, and then anything else is showing up. So a lot of these off loadings are really small. There's just one here that's kind of large. So it's doing a good job. And then the interfactor correlations, we can see that factor 4, which is this depressive affect, and factor 1, the somatic symptoms, are really highly correlated. And that's another reason why sometimes you get a 3-factor solution versus a 4-factor solution. If 2 factors were correlated 1.0, they'd be the same factor. So this is getting pretty close to that. So effects of some other options. This is an unrotated 4-factor model, and you can see that it's just like, it's not very useful. It looks like the 2-factor solution, basically. But there's nothing going on over here. So unrotated factors, probably not what you're ever interested in. This is an example with Varimax. So this is an orthogonal rotation, and this is a 4-factor solution. And what we get is a little bit of a mess, because what's happening here is you're not allowing the factors to be correlated. We know from previous models that our factors are fairly correlated. So the misspecification of this model has to be compensated for by allowing for these stronger kind of correlations that are, off of the target here. And also what happens is we've got this first factor, which is a combination of depressive affect and somatic symptoms, and then a separate depressive affect factor. So we're not even recovering the same 4 factors that we would if we had an oblique rotation. So a lot of times Varimax rotation does a pretty good job of working versus oblique rotation. And so some people therefore think, why not just do a Varimax? But there's no reason usually to specify an orthogonal rotation. And in this case, it kind of backfires. So we're getting to the conclusions here. So in general, The choice of your number of factors should be based upon theoretical appeal, parsimony, clinical experience, as much as empirical model fit. And here we're talking about EFA. So you're searching for the number of factors in this circumstance, but it's not all about empirical model fit. You need to be able to, your factors need to make sense. And so I think you should kind of qualitatively or subjectively and objectively, empirically consider multiple factors if you're in an exploratory mode when determining the number of factors. And I also want to emphasize, if you're exploring the structure of multi-item instruments, then use factor analysis, not principal components analysis. Use oblique rotation. I would use maximum likelihood EFA, which allows you to calculate CFI, because I think it's really, this particular example didn't highlight how much better it is, but it's usually a lot better. And just also that even, in general, working with measurement models should be a very deliberate process. It's not like a throw in the kitchen sink and start fitting models. You will probably run into some trouble with that. It's better to have a top-down approach. Think about the constructs you're trying to measure. Even if it's secondary data, there may be some items that from an existing measure that you just think are bad items. And if so, you may want to get rid of those. So, just think about it kind of from a top-down perspective, starting with the constructs and what they really mean. And in general, if you're conducting EFA, hopefully sooner or later you're going to continue with this work. You may make some refinements to an instrument, whether it's something that you created yourself or something that's off the shelf. You may need to adapt it for a new population group. So all of this is programmatic work. It's not project work. And so a lot of times you're going to bring qualitative methods into it, including cognitive interviewing after you have a draft instrument, or focus groups or individual interviews to help you identify whether you're on the right track with the constructs. Sometimes you take an instrument off the shelf and you try to adapt it for a new population, and you find that, okay, yeah, sure, all those constructs are fine, but there's another construct in this population group that never really revealed itself in the other population groups that is important to your group. And so you may need to create a whole new set of items to represent that construct when you're doing an adaptation. And then, it's always good to have replication and confirmation. And sometimes even beyond adaptation, sometimes instruments go out of style, so to speak, especially with like attitude measures. What was a kind of prevailing attitude in the 1970s may get like a full-on laugh today. And so sometimes society has moved in such a way that items lose relevance and need refinement. So another thing to consider. Having said all of that, I find EFA can be very frustrating, especially with large models. If you've got lots of items with lots of factors, it can really be frustrating. And mostly it's just because of this kind of what's in the simultaneous challenge section here. You have to determine which items to drop, but extraneous items can obfuscate the factor structure, and you have to determine the number of factors to extract. And if that's wrong, then an important item can appear to be extraneous. So it's really a big mess if you get yourself in a situation like this, because it's kind of like you don't have any bearing, and so you kind of spin around in circles with it. And I'm not really satisfied with any of the rotation methods. I don't find that one always works. And sometimes I find that maybe none of them work very well for me, although it could just be that there's nothing would work, conceivable or otherwise in some circumstances. But it's just frustrating because, you know, I find myself, it's like I'm unsure of the items that I'm working with. I'm unsure of the number of factors, and I'm unsure of the rotation method. So there's a lot to be unsure about. But when I knew about VARCLUS forever because it's been part of SAS for decades, but I never looked at it because I never took it seriously until one day I just tried it and I was just completely blown away. So I think VARCLUS addresses a lot of these problems that are addressed on this slide with EFA. And so that's why I wanted to talk about it next month. And I think that's it. So I don't know if I have, no, I don't have any questions at this point.
Little clapping icon. There you go.
Yes, thank you so much,
Thank you,
Steve. I do see one question here in the chat, maybe a couple of questions coming through. Here's the first one. Question for the speaker. What do you recommend for 1, generalizability, and 2, minimum sample size requirements for EFA?
I see the minimum sample size. Where's the generalizability?
It's all in the same question from Jesse. He asks, what do you recommend for 1, generalizability, and 2, minimum sample size requirements for EFA? And then there might be a second question after that from Amy.
And the question is that even
and then
relevant?
We can work our way through maybe.
Yeah, you know what's really weird is I don't see that from Jesse at all. Huh. So I'm just wondering about the.
It may have gone just to you, Rochelle.
Oh, it is.
Yeah, I don't know. I don't know what. Okay, so for sample size, so there's a lot of rules of thumb out there that about sample size per item or sample size per regression parameter in a linear regression. And I'm pretty sure that no one knows where any of those rules of thumb came from. There are some textbooks like in the 50s and 60s that included those, but they don't refer to where those came from. And so some of those rules of thumb got propagated on and on and on. In factor analysis, you'll often see people say, you know, that the sample size needs to be, you know, 200 or 300 or 400 or something like that. But a well-fitting factor model, if you really got, you know, good items and the right model, you can fit that model with less than 100, you know, respondents. There's, you know, like, there's just a bunch of examples like Lizroll, when you're fitting a confirmatory factor analysis model, can issue some warnings about the number of parameters being too large for the sample size. But there's been a lot of work that shows that that's really not a concern per se. And it's the same kind of thing as, you know, you should have 10 sample members for every regression parameter in a regression that you're going to, you know, regression model that you're going to fit. I mean, I think Eric Widdinghoff did do some work related to this, where he showed that there was some kind of rules of thumb that made sense. But for the most part, those rules of thumb, I just don't worry about them. For generalizability, I don't know what the question is. So, Jesse, can you elaborate on the generalizability question?
Well, I think you answered that question. I'm now recalling it, about how the factor loadings, or what you found back in the 70s, for example, is no longer apropos in our timeline, and so you really have to redo on a new population if you want to generalize to that population, whatever the results are. Yeah.
And it looks like we have another question from Tor as well. I don't know, Tor, do you want to ask your questions, or shall I?
Oh, the binary and ordinal.
There we go. Yeah. What approaches do you like when items are binary or ordinal with few categories?
With binary, you know, in the kind of factor analysis model where you're dealing with linear, a linear model, which is any EFA model that's like in a canned program that would be in a major statistical software package, is going to be a linear model. And so you can try to do things like input tetra correlations instead of Pearson correlations. I mean, you should probably never try to calculate Pearson correlations between binary variables unless the distribution of those variables is highly similar, because you can just show that if you've got like one variable is skewed left and the other variable is skewed right, then the maximum correlation that can happen between those variables is really, really small. So doing something like using correlations makes sense, but those are so noisy usually that I think there's a lot of noise that gets added in. So I just really try to avoid doing factor analysis of binary items, to tell you the truth. I mean, you can do it, and I would say use correlations, but realize that if you're running into frustrations, it may be because of the noise that's been introduced in your correlation matrix. For ordinal with at least 4 categories, I just go ahead and treat them like they're continuous. I know there's some work in CFA that shows that you should be careful about doing that. I think especially when you're testing the invariance of a solution across population groups and other kinds of things like that. But I just blast ahead if it's 4 or more. I mean, I usually like to have 5 ordered response options, but 4 is not that bad. 3 is that's pretty limited, and so I try to discourage folks from using 3 categories for items that would be later subject to a factor analysis.
Great, thank you so much. I see another question, you may be seeing it as well. I'll just read it from Rebecca Scherzer. Can you talk a bit more, please, about how you compare different oblique rotation methods? I assume you're looking for solutions where an item uniquely loads on one factor, where a factor has a minimum number of items loaded to it.
I'm not sure I understand the question, but I mean, with the oblique rotation, you're just trying to maximize with any rotation, you're trying to maximize the relationship between the items and the factors, and to find, while at the same time finding distinct item clusters. If you have an oblique rotation, it allows you more latitude in identifying item clusters, because you're not forcing your axes to be orthogonal or at 90-degree angles. And we just had a nice 2-factor solution. If you have 8 factors, then you're rotating axes in hyperdimensional space. So it's more than just two axes at a time. But the idea is to try to locate item clusters, and you're just going to do a better job of that if you allow the axes to kind of freely locate without imposing some kind of orthogonality to them. I hope that answers the question. If it doesn't, let me know.
If you'll humor me, I'll just read this as well for the sake of the recording. So there's another related question from Amy. I've used Quarterman rotation performed on a polychoric correlation matrix based on literature that says that Quarterman rotation ensures that clusters of variables are independent and easily interpretable, and polychoric correlations provide unbiased estimates. Is there any reason not to use this rotation option and type of correlation matrix every time?
Yeah, so if a rotation method is working for you, then that's fine. I probably have used Quarterman in the past, and I can't exactly remember what it is or how it functions. But if it works for you, then that's fine. Personally, I've not found any one rotation method works for me every time. Sometimes Promax works better than Harris-Kaiser. Sometimes Harris-Kaiser works better than Promax for any given application. In terms of polychoric correlation, so you're talking about ordinal response options, and so depending on how many response options you have, again, if I had 4 or more, I would just use regular covariances or correlations because it's less noisy. So polychoric correlations may be unbiased, but that just means that asymptotically unbiased. So how big does your sample need to be to ensure that you're not introducing noise because of that particular estimation versus using regular covariance estimates. So, again, if it works, it works. The proof's in the pudding, and so I don't have a problem with it. But and I will admit that I have tried working with tetrachord correlations, which mean binary responses, more than I've experimented with polychord correlations, because usually when I have 4 or more response options, I just go ahead and work with the correlations or the covariances. So my experience may not be, very informative for that, but and I think a lot of it depends upon, again, how big your model is, because if you're working with 60, 70, 80 items, then you can have a lot of challenges regardless. And so, but if you're working with, 5 or 10 items, then a lot of times it's a little bit easier to navigate the EFA modeling system without running into too much frustration. So if it works, it works. But, in general, whenever I fit an EFA model, the next thing I do is I fit a CFA model to the same data. And because that gives me a better set of tools for assessing model fit, even though it's not a true confirmatory analysis, it gives me information that is going to be helpful for me to understand how well things are going, and also what it might lead me to make additional refinements to the empirical model, and probably give me good guidance for where to go next if there's any idea of having a revision to the instrument and another kind of sampling of individuals with the revised instrument. So, part of it is, in my opinion, is not stopping with the EFA, but going on to a CFA.
Thank you, Steve. That was terrific.
I think there's more questions.
Yeah, there are more questions. I let people ask them, but I wanted to apologize for not introducing you. You jumped into the water too quickly. So we'll do the introduction next time. Okay,
that's fine.
Just means that Steve's so famous, he needs no introduction.
Oh, yeah. That's it.
So true, yes.
So what are the other questions?
Well, so So there's a question from Jesse about other models. So like for binary outcomes. So, you know, typically people make a big distinction between IRT, item response theory, which is, you know, basically originally developed for binary responses, and a lot of times in education settings where they're trying to penalize people for guessing and things like that. And the IRT proponents make a big deal about, you know, non-existent differences between factor analysis and IRT models. Basically, you can create a factor analysis model that is looking at, instead of linear relationships between factors and items, you can look at logistic relationships or you know, ordinal logistic relationships. And the M+ program has done a lot of that. You know, and there's IRT programs that look at binary outcomes and also consider ordinal outcomes as well. So there's really no big difference between the confirmatory factor analysis and the IRT modeling framework. It's just kind of the imagination of the software developers in terms of how far they're going to take it. But, you know, if the CFA modeling framework fits your needs, I think that the software is a little bit more developed when it comes to some advanced applications like testing the invariance of models across population groups and things like that, which can be important when you're doing any kind of, you know, disparities work, health disparities, and you want to know whether or not an instrument is really measuring the same thing in the same way across population groups, or any kind of comparative, you know, research where you're comparing people from different countries or cultures or whatever. You know, I would just kind of lump the EFA and the CFA under the common factor model, or the, you know, factor analysis model, and all the IRT stuff under IRT, but really they're all part of one larger umbrella, which is just, you know, measurement models that have latent variables and observed variables, and they can really, if you flesh them out, they can deal with, you know, you've got generalized linear models. You can create a program that would, you know, for Poisson items if you wanted to. So it's all possible.
Susanna would like to know, will response patterns impact the EFA? For example, response options range from 1 to 5, and many people are selecting 4 and 5.
Yeah, so that's like, so one of the distinctions that is more prominent in IRT is item difficulty, and in factor analysis, that the item difficulty issue is often not as prominent. And so typically, if you have an item that everyone's given a 4 and 5 to, that just means there's less information in that item. It means the item is easier to answer a 4 or 5, where some other item, you know, is like, you got a range from 1 to 5. So you might ask yourself whether or not that item is worded in such a way that it's providing as much information. Because, you know, if you had an item where everyone said 5 or everyone said 3 or whatever, there's no information there. So you might want to think about rewording that item or getting rid of it. And the same thing can happen, like I was talking about attitudes over time. You know, you could have an item that in 1972, you got 1 through 5 responses to every day. But in, you know, 2020, you get, you know, most people agreeing with it or disagreeing with it. So these things can change over time.
Forrest
Yeah.
put a nice reference in response to that question in the chat as well. People
Okay.
look there.
Hope I answered the questions.
Certainly feel welcome to unmute and ask if you have a question you'd like to ask live of our wonderful speaker today.
All right, well, hearing no questions, no further questions, I'd like to thank Steve. Please join me in thanking Steve for this fantastic presentation. I've been using factor analysis for like 30 years and I've learned new things from this talk. So thank you, Steve. This was awesome. And we're definitely looking forward to part 2 on variable clustering. And that is going to take place on April 13th at the same time, 11 to 12:30. So for those of you who are interested, please do make a point to attend that session as well. From what Steve said, it seems like it's going to be a newer method that, new for most of us anyway, I think that can be very helpful to us in our work. So thank you again, Steve.
All right, thank you all. Bye-bye.
Thank you, Steve.
Okay.
Thank you. It's great.
And thank you, Rochelle, for everything.
Thank you,
My
Rochelle.
pleasure. My pleasure.